So, good morning. Today I am going to discuss one important aspects of the surface chemistry, that is capillary action and Young and Laplace equation. You all know that the molecules of liquid tend to adopt area. Therefore, most of the liquids is just like a spherical in nature. And now if you want to understand the capillary action, so it is just if I take a pot and put a thin tube, so there is a flow of liquid, and this is basically called the capillary action. And the Laplace and Young equation is based on this capillary action, and this is called the curved surface. Now if I take water, I will see such type of thing. You know, formation of a meniscus. But if I take mercury, I'll find this type of shapes. Now, meniscus you can call it like that. So this capillary action is dependent on surface tension and adhesive and cohesive forces. Now, the fundamental rules is that when adhesive forces, that means the molecular attraction between a molecules and the wall of the tube, that is called the adhesive forces, and the interaction between the similar molecule, that is called the cohesive forces. So therefore, for the normal water, if the adhesive forces is greater than the cohesive force, so there is a rise in liquid. And today I am going to discuss the very important equation, that is called the Laplace equation, which gives some elementary idea about the capillary action and the curved surface. And this is, you know, that when there is a capillary rise, so there is a minimization of the surface energy and the surface area. So we will also measure the surface area and surface energy. So as I already discussed with you, that adhesive force means the attractive force between different molecules. Like I have already told you that this is a tube, and suppose there is a water molecule, so the attraction between this water molecule and this glass tube. Whereas if it is a cohesive force, so it is between the molecules of the same types of water and water molecules, and definitely this cohesive force induces the surface of the liquid contract to the smallest possible surface area. That is called the surface tension, and always there is a upward pull and inward pulls, and there must be an equilibrium between this upward pull and inward pull. So this is the schematic diagram of this two types of force, adhesive and cohesive force, and this is only for the water, And here this is capillary tube, this is one liquid, you can call it as a water. And the angle between the tangent of the liquid surface, so actually this, and the surface is called, this is actually contact angle. This is actually called the contact, which is very important. And if this contact angle here, as you see, if it is less than 90 degree, then the fluid will be raised. And if this contact angle is greater than 90, so it will suppressed for mercury, like that. So with the help of this Laplace and Young equation, we are also able to calculate this height of this meniscus. This meniscus, we can actually, if you take a glass of water, so you will see such type of things. So there are two type of pores. One pores. So if I take a droplet, or if I just the shape of the liquid droplets and the behavior of the capillary action, and it is pressure dependence and curved surface, and the pressure difference across the interface of the two liquid. Now if I take like that, so there is a possibility of this. Suppose this is like that. So there is a possibility of the P external and another is P internal. External pressure and internal pressure. And at equilibrium, the P external may be equal to the P internal pressure. And it is also depends upon the surface area as well as the surface tension and other things. And that type of equation is called the Young and Laplace equations, because this equation was derived by the two scientists. One is Young, another is the Laplace, and they have published this paper in Royal Society of the London Philosophical Transaction in 1805. And Laplace is also published like that. And in one sentence, you can call that this Young-Laplace equation is the basic law of capillarity, or you can call it Young-Laplace equation is suitable for the curved surface. Let me derive this equation, but before I go to the derivation, I just want to tell you that this is the equation actually. P internal pressure, or you can also write like that, P internal minus P external is equal to 2 gamma divided by R is the radius. Always remember that here you are considering that this water is just like a droplet, spherical droplet. So that radius is important, and so you can understand that this pressure relations with the radius. If we increase the pressure, of course there must be a change in radius. I'll discuss at the end what is the role of pressure and what is the role of this radius. So this is actually called this Young Laplace equation, relationship between the surface tension, because surface tension also is there, as well as the radius and the external pressure and internal pressure. Now, if the surface of a liquid is curved, there must be a pressure difference, that is called the Young Laplace equation. Now, the students sometimes get confused about the Laplace equation and Kelvin equation. Both are related to the curved surface, both are related to the capillary action, but Young Laplace equation is related to the pressure difference, and today I will not discuss the Kelvin equation, but the Kelvin equation means if the surface of a liquid is a curve, the equilibrium of vapor pressure of the liquid must also change. That is Kelvin equation. But today I am going to discuss the Young Laplace equation. Now, the derivation of this Young Laplace equation, there are certain assumptions. First assumption is that, as I told my initial statement, that liquids minimize their surface area, and therefore there is a formation of the curved surface, and that is therefore liquid drops are the spherical, and there is a, if I want to measure the surface volume ratio, it is also very, very small, and this cavity curved surface depends upon the pressure inside the cavity and outside the cavity. One is, as you know, that one is convex side, another is the concave side. Force due to the external pressure. Once we calculate the force due to the external pressure, it is called the inward force. Similarly, there is a change in force due to the surface tension. That is actually called outward force. And the last step is that the equilibrium between these two forces, external pressure and internal pressure. And I have taken this derivation from the book of the Peter Atkins. So now just we consider that this is two phase and suppose this is external pressure and this is internal pressure, and it is because consider it is a spherical in nature. So first we will calculate the force on the surfaces of this spherical cavity, and the radius is r. So let me derive these equations. So I'll do the derivation. First is the calculation of the force due to P external pressure. and that can be calculated by simply area into pressure. So area is, 4 pi r square, and external pressure is, if it P external. So that is the first part. Second, calculation of the force due to surface tension. As you know that when there is a external pressure and internal pressure, so there is a change in the surface area. And if I consider the surface area is this, so change in surface area is equal to, there is small change in radius, that is from r to dr. So I can 4 pi r square, change is r, plus small changes dr. Okay. Actual area is 4 pi r square. So I can calculate like that. A square r square dr square 2r dr. A square plus a plus b square. So I can write it is 4 pi r square like that, plus 4 pi dr square, second derivative, plus 8, 2 into 4, 8 pi r dr minus 4 pi r square. This 4 pi square is cancelled, and this I can ignore this second derivative, very small value. So what I will get is equal to 8 pi r dr. But we have to calculate the force. Determination of force or the evaluation of force due to change in surface tension. So therefore, we all know that very common formula, that the work is change in surface area as well as the surface tension. It is surface tension. This is. So therefore, dW is equal to, we can write it, 8 pi r dr, yeah. And force into displacement force into displacement equal to work. Force into displacement is equal to work. So therefore, I'm sorry, just the changes. work actually, sorry, work. If I want to just ability to do the work, so that is actually force into displacement. So therefore, if I want to calculate the force, work divided by displacement. So work is here 8 pi r dr divided by dr, small changes. So now the the force is equal to eight pi r gamma, right? So now once we calculate the evaluation of force due to the change in surface tension, we have already calculated the force, evaluation of force due to the external pressure. Now total outward, total inward force due to the external pressure. So it is 8 pi r due to surface tension plus we have already calculated then use the red color 4 pi r square and p external. So now we can remove all the things except these things. So first part is over. Total inward force. So last step is that there must be an equilibrium between inward force and outward force due to the internal pressure. That is 4 pi r square p internal. So there are two equations. One is outward force and another is the inward force. So we have to balance these things. So let me write 4 pi r square p internal is equal to 8 pi r gamma plus 4 pi r square P external. So I can write like that P internal is equal to, so this is divided by 4 pi r square. This is divided by 4 pi r square. So P internal is equal to 2 gamma divided by R plus P external. Therefore, the final equation that means the change in pressure, difference in pressure, it is inversely proportional to the radius. If the pressure is very high, you know that if I plot a graph between the radius and the pressure, so it becomes infinite. If it is high, it is low. If it is low, it is high. So I can write like that: P internal minus, I write P external is equal to 2 gamma divided by R. This equation is called Young and Laplace equation, the relationship between the internal pressure and external pressure, how the size of that liquid drop depends on these things. Now, if you understand this Laplace and Young equation, we can also calculate the this is the angle of this angle of this. So there are two forces. There is also I'll explain these things. Sometimes it is resultant is R. So one is R sine theta, R cos theta, like that. Well, I'll explain these things. But before that, let me first explain the significance of this Laplace equation and the application of this Laplace equation, that we can calculate the height of this meniscus. That is important. So now if I just want to see what is the relationship between this Pi minus P external 2 gamma by R. Yes, this is the final conclusion, that as I have written here, P internal pressure minus P external pressure or outer pressure is equal to 2 gamma surface tension divided by R. So what does it mean? As the difference in pressure decreases to 0, the radius of the curvatures become infinite. That means if I plot a graph between radius and pressure, and if it is 0, then it's just like this, like increasing. So it is like that. Like that. What does it mean? This 1, 2, 3, 4. Because it is one relationship between the pressure and the radius of that curved surface. But these different types of curve shows the different types of the surface tension. Because if I take water, the surface tension is different. If I take another liquid, the surface tension will be different. Now the last part, the application of this equation, that's with the help of this equation, one can calculate the height of that meniscus. That is the application part. And there is another equation that is called the Jurin equation. And with the help of the Jurin equation, one can calculate this thing. Because this you can call it a delta P. change in pressure is equal to 2 gamma divided by R. And you all know sometimes pressure is also, change in pressure is also dependent upon H, D, G. H is the height, D is the density, and acceleration due to gravity. If you equate these two equations, 2 gamma R equal to H dg, so you can also calculate the height of that meniscus. If you know the pressure, you can also calculate the, if you know the internal pressure and the external, you can also calculate the surface tension. The last part is that how we calculate that the height of that meniscus. Sometimes there is a possibility of the numerical problem for that. So we use the Jurin equations like that. And as I told you, that you can also calculate these things also. Meniscus and other things, resultant. So this direction is also possible. So there are two types of force. One is, if I just, so upward pull, and due to surface tension. So we have to again balance these two forces. This is the simplest equation for calculation of, this is due to the surface tension, pi r square h dg. H is the height, this is density, you can call it, you can write like d also. And here of course it must be in gamma. So 2 pi r gamma cos theta resulting. So if I just equate these two things, that means if I write like that, 2 pi r, this is the work due to this thing, weight of that liquid, 2 pi r gamma cos theta equal to pi r square h, even you can call it the density d like that. So you can calculate the h by that formula. So this is the first part. Upward force, here you can write gamma, you can write also. This is surface tension actually. And the weight of this, pi r square h. So if I just compare these two things, 2 pi r gamma cos theta is equal to pi r square h. If I simply g, here suppose this is gd, so h is equal to, you can just 2 pi r gamma cos theta divided by pi r square d g. So this, so 2 gamma cos theta divided by density and g r. So 2, I can write like 2 gamma cos theta divided by r, radius, density and g. So this is the formula by which you can calculate the h, also like that. And that is also called the Jurin's law, the same equation, 2 gamma cos theta, radius, acceleration due to gravity, and this is density of that liquid. For water it is different. So this is the application of this. So similarly we can also calculate the Kelvin equation. So today I have discussed the very simple Laplace and Young equation which denotes the capillary action for a curved surface. Thank you.